Hello, today I would like to introduce a paper, Infer Metabolic Directions and Magnitudes for Moment Differences of Mass-Weighted Intensity Distributions. My name is Tobang Li. I studied in quantum technique and taking Berkeley courses now. Indeed, this paper is the first paper that I started to rethink about how to address the replicability issue in biology. In the beginning of 2020, at that time I was in holiday, and the first time I think about this issue is in 2018. At that time, PNAS published a series of papers discussing the replicability and reproducibility issue in science. And later, the NAS published a book about reproducibility and replicability in science. And if you, according to NAS definition, the replicability is obtaining consistent results across studies aimed at answering the same scientific question, each of which has obtained its own data. And if you, after you read this sentence, I mean, the first few you might think about this issue is biology, right? Yes, I think most of them might think biology. Because everyone, I believe everyone who learned biology have such experiment. If you want to search some pathway changes or metabolic changes after a treatment, you might find that, well, there is sometimes that this paper saying that after this treatment, this metabolic upregulated. In another paper, is saying that, oh, after the same treatment, but this metabolic, it is downregulated. This issue is pretty common. So, I mean, Nature also often, they publish some comments or opinions about this issue. Replicating scientific result is tough but essential. And you can see that the chances is pretty low. If indeed it is a very low chances that successfully replicable. And so, although they are reproducible, because reproducibility is just it is just you can reproduce the same experiment, right? It does not require the consistent result. So, replicability is a more advanced definition comparing to reproducibility. And so at that time, because I was studying metabolomics, and then at that time I started to think about first is how to address the issue in metabolomics. And in metabolomics, that we normally the first approach that in 2018 at that time, indeed it's not my approach, it is the community's approach. Is that, for example, there are two samples, sample 1, sample 2, they are belonging to different treatments, and compound A, A1, A2, A3. And then you sum all this. Maybe they are different, but they are belonging to the same organic class. For example, lipids. And then you sum all these concentrations. That means although we cannot draw a conclusion, for example, maybe one this is upregulated, downregulated. Maybe if we just saying A1, A2, A3, this upregulated, downregulated, they are not replicable after a treatment. But if we sum all of them, we get the sum overall concentration, and then we see that it is downregulated. And then this conclusion is often much more replicable. The result is more consistent comparing to a single metabolite. In statistics, it is pretty easy to understand because it is, for example, if we saying that one metabolic, the lipids, possibility of lipids after treatment, there are 40% chances it upregulated, 60% chances it downregulated, and then you can see that it is an independent trial, right? And then after trial, so after more and more trials, and then you can this possibility will ultimately reach 99%, right? So if when you sum more metabolites, the possibility that you get the results, the overall changes that you get, it is more likely to be a highly confidence result that it is replicable instead of comparing you just draw conclusion for a single metabolite. So indeed, this is a pretty common approach in biology that we do some more experiment to summing more results and get a more consistent results. And in metabolomics, and there is a bottlenecks that, but in metabolomics there is a different. Because metabolomics is that metabolomics is that we do some we use some chromatography to separate the moleculars in the sample, and then heat each molecular using mass spectrometry. Maybe you use liquid chromatography or gas chromatography, but their affinities are different. Anyway, they all use some mass spectrometry to heat those molecular and then generating a mass spectra. Many mass spectra, many mass spectra, and then this mass spectra you can, and then you comparing them to the spectra in the database, and then you comparing the spectra because the database, the structure in the database is using some pure samples to generate, right? So you can, and then you're computing a similarity score, for example. Yes, you're comparing a similarity, you're comparing these two spectra, comparing the spectra you obtain in the Nature product, and then comparing to the spectra in the database. If the similarity is very high, maybe 99% accuracy, and then you can say, oh, these two spectra are nearly identical, so their corresponding compounds should be the same. And then you can say, and then you can find the structure of this the compound that producing this producing this spectra, right? So this is a standard approach, but the bottlenecks of this approach is that yes, for example, you can compare the spectrum in the library to the analyzed compound, but the bottlenecks of this approach is that because it is highly depending on the database. However, in the database, the spectra is very limited, very limited. Because I mean, for anyone who learn organic chemistry, you should know that the possibility of combinations of all possible organic compounds, the number is much more than the stars in the universe, and And so if you're just comparing, if you try using this approach theoretically, it is impossible for the database to exhaust all possible metabolites that in the nature products. That indeed there is only a very small, like this is only 2,500 metabolites, and this is a very small percentage of all metabolites in nature or in human. And indeed, now for all mass spectra we generated, it might be hundreds for GCMS, gas chromatography, mass spectrometry, or thousands for LCMS, but generally there is only 10%, at most 30% mass spectra that we can find their corresponding structures. So this is this is a method that we can find. So this is the difficulty that although we cannot find their corresponding, although we can generate their spectra, in most of the time we cannot find, we don't know their exact structure, because we cannot find the corresponding spectra in the database. And how to address this issue is a pretty hot topic in mass spectrometry study, and I post yes. Indeed, there are three main approaches. The first approach is based on the spectral similarity, and this is first proposed by Lowry in 1977 in analytical chemistry, and it was already developed for half century. And for example, the popular GNPS, you can see this is you computing the basic principle is just like that. You're computing the spectral similarity between two different spectra, for example, like this. And then if there is a high similarity, maybe for example 0.9, and then you're placing very close. If it is related far, you're placing related far. If it is not, maybe 0.1, and then you're placing very far. And then after you're placing this, you can generating a network like this. This is a network, right? And then after you generate such a network, and then maybe, for example, this is and then you can find there are several clusters, right? For example, there is a cluster. And then maybe, for example, maybe this compound we don't know the structure. Of course, here we know, but maybe sometimes we don't know the structure. But we know the nearby spectra. We know this structure. For example, it is like this structure. And then maybe we can conclude that this spectra, because it shares a very high similarity to this spectra, so they might have a similar structure. Indeed, you can see they have, right? The structure, it is highly similar, or this. Yes, or this don't know. Yes, this we don't know the structure. Yes, like this. Yes, right. You can see that all these nearby compounds, they have a pretty similar structure, right? So we can just and then this we don't know the structure, but we can basically conclude that it should have such a ring, have such a yes, right? Although maybe it is not exactly, of course, it is not exactly identical, but otherwise the spectral might be the same, right? But it should be very close. So in this way, we can basically classify the spectra into several classes according to the clusters that we generated in the network. And this is a very computationally pure. It is purely based on algorithms that we based on the similarity measures that we done, and it is a pretty bioinformatics approach, and without requiring any analytical chemistry, right? Analytical chemistry, organic chemistry knowledge. And there is another approach that the landmark paper is this paper, SCI Finger ID, and this published in PNAS. And this paper is that instead of we classifying the spectra into several classes, we can directly predict the molecular structure, and based on the fragmentation tree and machine learning. And this is indeed also even now it is a very hot topic, and they are mainly based on machine learning, so some neural network. This is this finger ID is that if we get a spectra, we first search the database. If in the database there is a spectra, and then there is a spectra. If we don't know the spectra, if there is no spectra in the database, and then they can synthesizing a spectra structure. For example, in analytical chemistry, there is often several peaks they representing. For example, in the fragmentation trees, that we first placing this compound in the network, this spectra in the network, and then we can predict it that this structure is very similar to the nearby structure, right? And then they started modifying the structure, and then getting a prediction result, predicted the structure. But I need to say that this result, this accuracy is not very high. Yes, and it is not very high. And normally we cannot draw a conclusion that from the structure based on the prediction. And normally we can only say that if the structure is representing, for example, a lipid, then we can say that this is a lipid. This spectrum representing a lipid. We cannot draw any conclusion about the exact structure based on the exact structure, because the prediction is that just if in the class level, organic class level, this prediction accuracy is relatively high, but in the exact structure level, it is although it can returning a structure, but this structure is often a pretty low. The accuracy is pretty low. And so and indeed there is recently. There is a new approach that a new approach that we inversely synthesizing the spectra that based on the structure. Here is using the spectra to predict the structure, right? There is another approach that inversely they can inversely synthesizing the structure based on synthesizing the spectra based on the structure of the metabolites. It is their work. You can search relevant papers, and mainly it is Durenstein's in his lab. And indeed, this way is that in this way that we can generate a much larger database, because there are many synthesized in silico synthesized mass spectra. And this approach, and then we search comparing the spectra with those synthesized spectra in the database. This approach is more accurate comparing to this predicting structure approach, and it is already currently a very hot topic. But you can also the same that generally you cannot draw conclusion based on the exact structure, because although it is higher, but it is still not accepted by the community. Yes, and you can only draw conclusion according to the class they predicted. And so indeed another approach is that instead of we predicting the structure, we just directly predict the class. And the Lehmann paper is this published in Nature Biotechnology, that they just directly use a neural network to predict the compound classes from the fragmentation spectra based on the LCMS spectra, and they reach a pretty high accuracy. This is a pretty high. And this paper, and indeed it is this paper and another paper, MassQL, and developed by Ming-Hsun Wang, and I was introduced by this paper introduced this tool in the late of 2021. And this Ming-Hsun Wang's approach is indeed a very novel approach. Maybe it is, if you're strictly saying that it is not related to these three approaches. That yes, maybe you can classify them into a new approach. But Ming-Hsun Wang's approach is that we can manually searching the peak in the spectra. For example, if you have some analytical chemistry knowledge, you may know that often a spectra is a peak. This peak often it is corresponding to a certain structure. For example, this might represent this is the C2 and H2. Anyway, this peak, because especially if it is a very high accuracy, you can know according to this peak, you can know the formula of this peak, and then according to the formula, you might get some structure related to this peak. So Ming-Hsun Wang's approach that we can directly search those peaks, and then for example we can search all peaks have this 71 this peak 71 mass have this peak, and then among thousands of spectra, you search all spectra that have this 31 peak. The relative intensity is higher than maybe higher than 50%, and it is and then you can classify this spectra into a class that this spectra all have a peak that is 71. And the relative intensity is higher than 50%, and then basically you can define a new class of compounds that their related spectra are based on their related spectra have such a characteristic peak. So that means that instead of we classifying compounds according to their structures, maybe we can classify compounds according to their spectra, right? This is yes, and this is a pretty novel approach, and they show that also we can combine relating to them to some analytical chemistry knowledge. For example, bromination, you are in the isotope that normally there is some because isotope there are several different peaks, or maybe 1, 2, 3, right? Some three, maybe 1 or 2, or maybe 2 or 3 different isotopes, and then you can search their relative intensity. If the relative intensity, if the relative peaks, the peaks, the mass relation satisfying some certain relations, and then we can say, this is related to brominated compounds. This class of spectra, and then first we search all these peaks that have such a spectra that have this, right, and then we can relate it to them to in analytical chemistry. They are related to brominated compounds, and this is a pretty novel approach that and it is mainly this paper, and also this paper let me realize that in classifying the spectra, we don't have much things that we can do, because if you say predict the analytical chemistry, organic chemistry compound classes, this paper already reached a very high accuracy for the LCMS data. And if we're saying that Ming-Hsun Wang's paper is much more flexible, because this paper can, although they have many classes, but these classes are defining classes, right? And MassQL, they allow that the users to define their own organic chemistry classes, and this is an advantage. Although I think there is still a very long way for his idea to be accepted by the community. But this is a very novel and a flexible way. And indeed, this paper, I realized that in classifying the spectra, we don't have much things that we can do. And if we say predicted the structure, and there is a thing that first that I don't think that predicted structure is very necessary, because as I said that if you say in replicability issue, normally for a certain structure, this result is often not reproducible. And also another issue is that if you predicted the exact structure, the accuracy, indeed, although there are intensive resources put in this field, but yes, for example, after that, already nearly 10 years passed, and but this accuracy is still relatively low. So I think there is still a very long way, maybe in the future, using some machine learning, yes, and more and more data spectra in the database. Maybe this can reach a very high accuracy, but at least at this stage, there are still a very long way that we need to do. And then I started to think about another aspect in metabolomics, that is the metabolic pathways. Because the metabolic pathways, and instead of classifying the spectrum, metabolic pathway is very different. You can see the metabolic pathway is a very complex network, and it has a direction. For example, here it is glycolysis. It is from glucose to pyruvate. There is direction. And more importantly, if you think about metabolic pathway, there are many difficulties. That first, if you want annotating, of course, first you need to know the structure, right? If you don't know the structure, how you find the pathway? Impossible. Even you know the structure, normally, because many pathways, they are not exist in nature. They are they are not. You cannot find the pathway database. You can see that in the pathway database that although there are many pathways in the database, yes, there are many pathways. But these pathways just representing a small percentage of all pathways that we found, and especially for some for example, human, the pathways that we know is already we study or some bacteria, E. coli, maybe most pathways, especially E. coli, maybe most pathways we already know. But for some relatively less intensive studied organisms, many pathways that we don't know, doesn't exist in the database. So indeed, according to my experiments, that maybe often only 50% metabolites that they have their structures that can be find their corresponding pathways. Now this is often the case, or maybe even lower, often lower. And more important, even we know the pathway. For example, here glucose pyruvate. Normally we can find we can find this glucose. In most cases we can find. But even if we know, for example, if the metabolomics data set saying that the glucose is downregulated, pyruvate upregulated, can we say this pathway glycolysis move forward? We cannot. Because metabolic pathway is a very complex network. The glucose is related to many different pathways. For example, pentose phosphate pathway or carbon fixation. It's related to many different pathways. So maybe this down-aggregated in glucose, it is related to some other pathways changes, and also pyruvate other pathway changes. And maybe although it's seemingly possible that we can say that this is out forward, but indeed maybe in the real world this may be some other changes, and this does not change. And so this is why that we often need some proteomics or transcriptomics data to further combine it with metabolomics data to draw some conclusion about pathways. And in most cases, if we just say in the metabolomics, we often in most cases we can just draw conclusion based on the concentration, the class changes or the concentration changes. We cannot draw conclusion from the pathway. Although if you read related papers, maybe some papers will draw such conclusion, but if you think about strictly, they are not, such conclusion is not justified. And so at that time, I started to think about whether it is a way that we can do something on the pathways that have a relatively high confidence that is replicable. And also at that time, a PNAS paper yes, in the early of 2022, and then at that time I read a PNAS paper. This is a totally different PNAS paper, but it is using a very elegant mathematical deduction. It's separating the association to direct association and indirect association. So at that time, I started to think about whether it is possible that we do some mathematical approach that we can solve this replicability issue in metabolic pathways in metabolomics. And then after I thought, I realized that indeed there is a common nature in this field. For example, in all the pathways, they can be classifying. Although maybe there are some pathway we cannot classify them into these two categories, but they are most of them they can be classified into biosynthesis and breakdown, or neapolism or catabolism. And they have a common nature. For example, if you have two molecules synthesizing to a anabolic synthesizing to a bigger molecular metabolic. Although this metabolic, we don't know that. Maybe it is represent many different metabolites. But there is a common nature that the mass will increase. The smaller metabolites, the mass of the smaller metabolites, it must be lower than the mass of the bigger metabolites, right? Because they're synthesizing. Also, if we reverse the direction, and then you can conclude that this breakdown, this catabolism, the mass will decrease, right? This smaller metabolites, it must have a lower mass comparing to the bigger metabolites, right? To the products will have a bigger mass compared to the original metabolic, right? So this is indeed, if we try to translate this mass relation to the mass spectra data set. For example, like here, we have a data set that this spectra, we don't know the structure, we just know the spectra. This is the intensity, and it is related to the concentration. And then this is this related to the and then this is this in front of the concentration. This is a mass, because for although we don't know the structure of a spectra, but most cases we know the mass of a spectra, because for example like this spectra, normally the highest mass peak. Or it is representing the mass of this compound they represent, or maybe sometimes because sometimes there are some peaks there, some small molecules there combining to this metabolic, so we need a minus a mass. But most cases, but anyway, that in mass spectrometry, that the mass of each spectrum can be very easily and very accurately. We can know that, and so that although we don't know the structure of this spectra, we know the mass. And since we know the mass, we can times the mass with the concentration, and then forming like in this way, and generating a mass-weighted intensity distribution. We call it intensity distribution. Is that, for example, sample one? If the sample one here this is intensity, and this is the spectra corresponding to a class, and then this can be formed a sample, right? This can be formed a distribution, okay, or a sample that a sample. A distribution. Maybe it is like this, right? Yes, maybe it is like this. Yes, maybe it is like this. And then we can and then we further use the mass weighted. Maybe it is like this. And then after you use mass weighted, and then you can say that, for example, this is sample, the mass weighted intensity distribution of sample 1. This is sample 2. This is low mass, high mass, high. And then you see that the location increase, right? Generally the mean increase. And then we reminding that if the mean increasing, the metabolic generally, of course, there are metabolic pathways. There may be constantly. There are some metabolics towards breakdown and some metabolic towards synthesis. But we can say that on average, just we say that on average, this concentration changes. We can say if this mass weighted intensity distribution, if the location increase, we can say that on average, the metabolic pathways it towards anabolic, it towards synthesis, right? It is anabolic. And if the location decreasing, and then we can, on average, it is towards catabolic, right? And indeed, if you think, because this is a mean is the first moment, and then if you think about higher moments, the shape of the distribution, you can even think about the standard deviation. Standard deviation, you consider the spread of this. You consider the spread of this concentration, and then you can see that, for example, here this spread, the sample 1. This is much. You can see that the standard deviation is much higher in sample 2, right? So what is the representing this standard deviation? It is basically saying that, for example, this is a for low weight to high weight, right? And then if you imagine there is a pathway that generally the metabolics from in the middle, this is metabolics in the middle. So metabolics have middle mass that is not very high and not very low, and then some of them will towards catabolic and towards breakdown into smaller metabolic, and some of them in the middle it will synthesizing to higher weight. And so if the metabolic direction is like this, and then you can imagine that generally this mass weighted intensity distribution, it must have a higher standard deviation, right? This is generally. So in this way, we can defining a new metabolic direction like this. We call it duobolic. If the direction is toward two different directions. And then if we saying that, for example, in the opposite, that for metabolics, low metabolics is synthesizing, high metabolics it break down, and then we can say that it is called duobolic. It is called centrabolic because it towards the center, right? So in this case, that we can predict that generally the mass weighted intensity distribution, the standard deviation should be lower, right? It should be low. As it should be low because most metabolics it towards the center, so the standard deviation will be lower. And so that means, so indeed, we provided defining two new metabolic directions, and this direction is based on a mathematical definition, a statistical definition, based on the mass spectra, based on the mass weighted intensity distributions, based on the mass spectrometry. This is the interesting of this approach, and indeed, if we can even consider higher order moments, for example, schooners or Krilasis, their biologically related biological meaning might be less significant. So we mainly consider these four metabolic directions, and indeed, after that, we can generate a table. For example, here we can generate a table For example, here purine, for the purine class, we use a location estimator. Here I use Hodges-Lehmann estimator because it is a robust location estimator. And in another paper, I further prove that this is the optimum approach. Yes, in this paper, robust estimation for distribution structures. It is not. I discussed that it is the why the Hodges-Lehmann estimator is the best choice. Because we need to use we need to use a non-parametric robust mean estimator, yes, to estimate this, and Hodges-Lehmann estimator is generally the best choice. And then you can see that, for example, this location estimator, this purine in the healthy group, it is relatively low mass weighted intensity distribution. But this is a COVID-19 data set. In the series of the COVID-19 patients, this is higher. And so we basically can say that this purine pathway towards synthesis, the purine synthesis pathway is upregulated, right? And this can be confirmed by previous studies and alliance. And so anyway that we can we can find the metabolic pathway changes. And for many pathways in these are just significant changes. There's a much bigger table. It have more classes, and we can know the pathway changes of many pathways, and with a relatively high accuracy, just using this approach. And this is medium standard deviation. It is a robust estimation of the standard deviation proposed by Bickel-Lehmann. It is also the optimum approach, and I also discussed in another series. Indeed, this is called. Initially, I called such a table. I called it directome. But you can also have a. But it is not just the direction. You can also get the magnitudes, because you can just minus this. And then you can standardizing it. You can have a magnitude. So you can also call it vector or momentum. Now I call it momentum because it is analogous to the momentum in physics. So I call it momentum. Initially, I called it directome, so I registered this directome domain in 2022, and because the reason I did this delays to 2 years is that because later I was most of my time was I spending in finding which location estimator, which spread estimator I should use in this field, and so I developed a series of robust location estimators. Of course, now here these are two previously approached, but if sometimes you can also use change this Hodges-Lehmann estimator to the medium standard medium Hodges-Lehmann mean. Yes, for example, here I also propose a medium Hodges-Lehmann mean. Yes, and you have a lower bias. Medium Hodges-Lehmann mean, you have a much lower bias comparing to the Hodges-Lehmann estimator is here. Yes, and anyway, this later because I'm focusing on theoretical statistics, so this paper was delayed. Anyway, but this is a very interesting concept that we defining a mass weighted intensity distribution, and based on that we provided a mathematical definition for the two classic biology concepts, catabolic and anabolic, and then we defining new metabolic directions, duobolic and centrabolic, and we show that in this way we can very easily infer the metabolic pathway directions based on the structure the mass spectra, and without knowing the structure of the exact structure. And if you are interested, feel free to contact me, and I hope they can be published soon. Thank you for listening.